Hello friends, this is Animesh and welcome to the Great Mantra. So in this video, okay, we are going to learn the working of the N Mosfet. Okay, so in last video we have seen the 3D structure of the N Mosfet. This is N Mosfet enhancement type N Mosfet, right? So here this is the gate, this is the source, and this is the drain. Okay, so here source and the drain is doped with a pentavalent impurity, right? Okay, pentavalent impurity. So that's why this is the N plus region, this is the N plus region, and the substrate, or we can say the body or the bulk, is doped with the trivalent impurity, that is the P type impurity. Okay, so here the source and drain is N type, and the substrate, and we can say it body or bulk, is P type. And here is gate may be the polysilicon gate or it can be the metal gate. Okay, and this TOX is the thickness of the silicon dioxide. Okay, this TOX is the thickness of silicon dioxide, SiO2, or we can also say this is the gate oxide, right? Gate oxide. So here the length of the channel is L and the width of the channel is W. Okay, right. So here this oxide, okay, this oxide is used for the isolation. This oxide is used for the isolation, or we can say this oxide is a field oxide. Okay, field oxide, and this oxide is a gate oxide. So what will be the difference between the gate oxide and the field oxide? Okay, so the gate oxide is formed, okay, by the dry oxidation process, while the field oxide is formed by the wet oxidation process. So here we can say that this dry oxidation is, okay, slower, and it provide a thin oxide, and its electrical property, okay, is, okay, good, is better than this field oxide, right? Okay, and the wet oxide, the oxidation, the SiO2 formed by the wet oxide is faster okay. Its thickness is thick oxide, it is a thick oxide, okay, and its electrical property is, okay, bad as compared to the little bit bad as compared to the this dry oxidation. Okay, the oxide obtained from the dioxide, right? So uh, so here in the dry oxidation we use the equation Si plus O2. Okay, this is chemical equation is SiO2, silicon dioxide. Okay, here Si, we use Si and 2H2O because of the wet oxidation, and here SiO2 and plus 2H2, right? So we have seen here what is the difference between the thick field oxide as well as the dry oxide. Okay, sorry, the gate oxide as well as the field oxide, and the gate oxide is formed by the dry oxidation, while the field oxide is formed, okay, using the field oxidation or using the wet oxidation, right? And we have seen that dry oxidation is a slower process, wet oxidation is a faster process. We can obtain a thin oxide by using the dry oxidation, and we obtain the thick oxide using the wet oxidation, and we have seen the chemical, okay, equation here. Okay, now, okay, now uh, here one things to know, why we are doing here highly dope, why we are using here highly, okay, highly impurity doped N type, okay, and why we are using the substrate as a lightly doped, okay, trivalent dopant. Okay, so why we are using here heavily doped, okay, heavily doped N type, and why we are using here lightly doped P type. Okay, we can also use in the for the drain and the source, okay, N type, and this is the n instead of the n plus. Okay, heavily doped, and we can use this as a p minus. But why we are using the n plus? Okay, n plus heavily doped. Why we are doing heavily? Okay, why we are heavily doping this source and the drain region? So here's the reason is the contact. Okay, this is the contact. If you see, this is the contact here, this is the contact here, this is the contact here. So these contact are the ohmic contact. Okay, ohmic contact. These contact are the ohmic contact. Okay, and since we are providing the contact using the metal, hence the metal have a large number of the free electron, and to match, okay, the concentration of electron with this concentration of electron of the metal, we are doing here heavily doped. Okay, heavily doped, we are doing here heavily doping, right? Heavily impurity doping to match the free electron concentration with the metal, right? So let's see the 2D structure. Okay, so 2D structure is like this. Okay, here we are using gate, here source, here drain. As we know that the source and drain are symmetrical, so we can interchange this source and the drain. But in the bipolar junction transistors, since the emitter and the collector area is not equal and their doping is also not equal, hence we cannot change. Okay, we cannot change the emitter and the collector in the BJT. But okay, but here we can change this source and the drain. Okay, we can change this source and the drain, right? Okay, now we are going to see the and now we are going to see the operation of the MOSFET. Okay, working of the MOSFET or operation of the MOSFET, right? So here, okay, here what I am going to do, I have drawn already the MOSFET here. Okay, to save the time, so I am writing the case 1 here. Okay, case 1, we are going to see the working of the enhancement type MOSFET and MOSFET. Okay, in the different cases. Okay, so that it will be easy to understand. Okay, it will be easy to understand, right? So let's assume our first case. Okay, what we are going to do here, okay, we are going to connect body or the substrate or the bulk with the source. Okay, so now I am going to do the connection here. We have connected this, sorry, we have connected this source with substrate. Okay, and we are putting this substrate at ground. First thing, why we are putting this substrate at ground, we are going to see. Okay, here, right? Now what we are doing, okay, in first case what I am doing, I assume that, okay, the VG equal to 0 volt. We are not applying any voltage on the gate, we are not applied any voltage at the drain. Okay, and we are also not providing any voltage to the source. That's why the source is connected to the body and it will be the ground. So here I am making both the source, drain, and the gate and the body at 0 potential. This means I am grounding this all the 4 terminal, like, right? So here as we know that, okay, here To understand the operation of this, okay, we have to understand when a p-type semiconductor okay come in the contact of the n-type semiconductor, what's happened. Okay, so now we are going to see what's happened when a p-type semiconductor okay come in the contact with the n-type semiconductor, right? So let's see what happened when p-type semiconductor come in the contact with the n-type semiconductor, right? So here I have taken one p-type semiconductor, we are going to see this more detail, okay, when we are going to cover our p-n junction diode chapter. Okay, this is the p-type semiconductor and this is the type semiconductor, right? So this is the p-type, the p-type semiconductor. This is the n-type semiconductor. Why these are why this is p-type? Because here we have dropped the silicon, okay, the intrinsic semiconductor or silicon, the pure semiconductor, okay, with the p-type impurity, okay, or the trivalent impurity like boron, okay. Here we have dropped the intrinsic semiconductor with a pentavalent impurity or a n-type impurity or a donor with the donor atom. Here we have doped with the acceptor atom, okay. Here the donor atom having the concentration nd, okay, per centimeter cube. Here having the concentration Na per centimeter cube. So we can see how we are okay, representing this. So this is the p-type semiconductor, right? So this p-type semiconductor is like this with the hole, okay. And this is the n-type semiconductor, right, having the free electron. So as we know that the majority charge carrier for the n-type electron n-type, the majority charge carrier for the n-type, okay, semiconductor is electron, and the majority charge carrier for the p-type semiconductor is hole, right, is hole, okay. So we can also say in this way, in the n-type semiconductor the minority charge carrier is hole, and in the p-type semiconductor the minority charge carrier is electron, okay, right. So here when we are going to okay connect this, connect not by wire in the physical connection, okay, we are going to contact this, okay, this both the p-type and the n-type semiconductor. When we are going to keep this in the contact to each other, okay, then what happened, let's see. Let me draw first. When we are going to put this in the contact with each other, what happened here, okay, this is the point of contact, okay. It may be one is bigger, one is small, but it's not like this, okay. So here what we have done, okay, let's see here, or let me give the more space here. Let me draw first the diagram. When we are keeping this both in the contact, what happens? Okay? So here the majority charge carrier is what? Hole. Okay, because this is the p type. Okay, this is the p type and this is the n type semiconductor. So let me draw here. Now we will see what happened when a p-type semiconductor come in the contact with the n-type semiconductor. This is the electron, a positive ion with electron. Okay, because a positive ion with for the n-type semiconductor, and for the p-type semiconductor a negative ion with hole, right? So when this p-type semiconductor come in the physical contact with the n-type semiconductor, and as we know that the concentration, okay, of the hole is more in the p-type semiconductor and the concentration of the hole is less in the n-type semiconductor. So because of the concentration gradient, the hole will move from high concentration to the low concentration, from high concentration to the low concentration. In same way, the electron is also moving from n type to the p type because of the concentration gradient. Okay, so when we see near to the contact of these two semiconductor, we will found that okay, we will found that when, okay, when the electron is coming, okay, from the n type to the p type, and when the hole is come from the p type toward the n type, the electron hole recombination will happen near the junction, and this electron will combine with this hole, this electron combine with this hole, this electron is combined with this hole, and hence the electron hole recombination happens here, and this region having only the immobile, immobile, okay, this region having only the immobile, okay, charge carrier or the ion, okay, which cannot move, okay, immobile charge carrier or the ion, and this region is known as the depleted region. Okay, and because of this a positive potential here, negative potential is here, and because of this a potential barrier, okay, or junction potential is developed, and due to the junction potential a built-in electric field is developed here, a built-in. So this is the working of the PMOS, okay. Because of the concentration gradient, the electron and hole will be, okay, will come from the p type to the n type, and the electron will come from n type to the p type, okay, and hole will become from p type to n type, okay. Because of this the electron hole combination will take place at the junction, and due to this the junction, near the junction only the immobile ion will present, and this region is called as the depleted region, okay. And because of this a barrier potential is creating, okay, v naught of junction potential we can say it's also, and because of junction potential or the barrier potential the built-in electric field is developed here, okay. So this is the basics things of the pn type diode or pn diode, okay, not pn type diode. This is the basic function of the pn diode, okay. Next we will see in this chapter in the PN junction diode, which we will cover separately, where we will see, okay, how this PN junction diode is going into the forward bias, and how this PN junction diode is going to the reverse bias, okay. And where there we will also see the energy band diagram, right? So we will cover this chapter later, okay, because the MOSFET is different, is very difficult. It look like difficult, that's why I am covering here MOSFET first, right? So as we know that and we have learned from here that when the p-type semiconductor come in the physical contact with the n-type semiconductor, so near the junction a immobile ion present, and this immobile ion is called as the, this region of the immobile ion is called as the depleted region, okay, depleted region. In the same way, see here, an n-type semiconductor is come in the contact with the p-type semiconductor, and here, since this is the heavily doped, we can say also this is a heavily doped, so here depletion region will be very less, okay, here depletion region will be more. In the same way, let me draw the depletion region, okay. Here let's see, this is the depletion region, okay, this is the and so this depletion region having the negative ion, right, it's having the full of the immobile ion, immobile negative ion. And since this is the heavily doped, okay, n type is heavily doped, so here is also exist, and here the positive ion will present, right, the positive immobile ion will be present here. And why the thickness is less, the thickness of the depletion region is less, since this is the heavily doped, okay, since this is the heavily doped, right, so this is the depletion, or we can say this is the depletion region at the drain and the source, okay, terminal, okay, right, at the drain and the source they will exist only depletion region when we will keep the source, gate, drain, body all at the zero potential, right. And since this is the p type and this is the n type, uh, we can also see like this, okay, we can also see like this, okay. Here exist a diode, a PN junction, here we can say like this. So this is the p type of, and that's why the positive terminal, negative terminal is the n, is the negative terminal, and this is the positive terminal of the PN junction diode. In same way we can also draw more, okay, diode like this, okay. There will be the large number of the diode, this we have seen. We have also seen here diode like this two back to back, okay. Okay, so this is called the, this is called the depletion region. Only the depletion region will be present here, okay, in the substrate near the SiO2 interface. Here we can say this as the silicon dioxide, okay, silicon dioxide interface or surface, near to the surface we can say interface, or silicon dioxide surface. So as we have seen that when we kept the gate at the zero potential, the drain at the zero potential, and we have connected source to body and kept it to the zero potential, or the grounded, so only the depletion region will be present here. And we will also see there is a number of the diode presented here, okay. So once more things here we have to understand that, okay, in any in any NMOS type MOSFET, in any MOSFET which is the having the p type substrate, okay, which is having the p type substrate, in any MOSFET, in any MOSFET means we can say that this is the N type MOSFET. The MOSFET having the P type substrate is the N MOSFET. Okay, so N MOSFET we can write here N MOSFET. Okay, N MOSFET having P type substrate, and the P MOSFET, okay, having the N type substrate. Remember these things. Okay, so in the NMOS, okay, in the NMOS we keep the body terminal or the bulk or the source or the substrate terminal at the less potential. Okay, at the less potential. So among all these four terminal, okay, among all these four terminal we keep the body terminal at the less potential. Why we keep this body terminal at the less potential as compared to this all the three potential? Because we want keep this diode, okay, this many diode, what diode present here, into the reverse bias. Okay, into the reverse bias. Why we want to keep this diode in the reverse bias? Because if we apply the some potential at the body, okay, then this diode will be in the forward region, and hence the large amount of the current will be flow through this, and hence our MOSFET will be burned out. This is the reason why we keep the bulk of substrate or the body terminal at the lower potential. Okay, at the lower potential among all these three terminals. Okay? Among all these four terminals, we keep this body terminal at the lower potential to keep this diode into the reverse bias, right? So here we have seen the two things. The first one, when the Vg will be 0 and the Vd will be 0 voltage, then this region of operation of the MOSFET is called as the depletion region. Okay, and the second things is we keep the body terminal, okay, for the N MOSFET at the lowest potential, because we don't want these diodes to be in the forward bias. Okay, now we are going to see the case number 2. Okay, here we are going to see the case number 2, right? So let's see this. So here what we are going to do, first make the connection. We are going to just connect the source with the drain. Okay, the source with the body. We are going to keep this at the ground. I am going to find this body with source, and I am keeping this at the ground. Okay, now what we are going to do here, okay, we are keeping Vg at 0 volt. This is Vg, this is not H. Vg at 0 volt, the gate voltage at 0 volt, and we are increasing the Vd. Okay? We are increasing the Vd. Okay, we are increasing the Vd, or we can also say that we are keeping Vgs because S is grounded, so we can say this S as a reference. So we have kept, okay, Vgs at the 0 volt, and the Vds we are increasing. Okay, so we kept this Vg 0 potential, and we are increasing this VDS, right? We are increasing this VDS. We have connected positive terminal with the drain, and the negative terminal we have grounded, or we connected with the source. This both are same, right? So here this will be the positive terminal. Here it will be the negative terminal, right? And this will be the VDS, and we are increasing this VDS. increasing this VDS. So what will happen here? We have seen that there will be the depletion region exist. Okay, there will be the depletion region exist. Okay, here the depletion region will be exist, right? We have seen that when the VG will be 0 and the drain will be 0, so here the depletion region will exist. Okay, now what happened here? We have also seen that here there was a diode. Okay, this will be the post. So when we kept this substrate at the ground potential and when we increasing the voltage at the drain end or the drain terminal, this diode will go into the reverse bias. This diode will go into the reverse bias. Or and when any PN junction diode will go to the reverse bias, okay, its only depletion region width will be increased. Its depletion region width will be increased. Okay, so in this way, when we are increasing the drain voltage, okay, the drain voltage, the depletion region width, okay, the depletion region width will increase here, and depletion region width will be like this. The depletion region width will be increase here. We can use the another depletion region width will be increase here. Okay, at the drain end, it's not increase, it's not change at the source end because we are not providing any voltage at the source end. Okay, we are providing the voltage only at the drain end. That's why the depletion region width will be changed at the drain end, right? So here id will be equal to 0, no current flow. Here no channel exist, here also id will be 0, no current will be flow, and here no channel exist. Now we have covered the two cases. Okay, now let's go to the our third case, right? So what will be our third case? Okay, let's see our third case, right? Let me erase this and we will write there. This is the plus region, this is also the n region of p type. Okay, right? So what I am doing here, let me write the case for 3. What I am going to do here, I am increasing the voltage at the drain and the source. Okay, I am increasing the voltage at the gate and the source. Sorry, I am increasing the voltage of the gate and the source, and we are applying zero potential at the drain end. Okay, we have applied zero potential at the drain end, and we are increasing the voltage at the gate end, at the gate terminal. Okay, so here let's make the connection. First, what we are going to do, we are going to connect the source to the body. We are making this at the zero potential. Right? Now what I am doing, okay, I am grounding this drain terminal, right? And I am providing the voltage, okay, at the gate terminal. So I am connecting this drain to the voltage. Okay, So this is the VGS. This I applied the VGS here, and we are increasing this VGS. So let's see what happened. Okay, let's assume. Okay, we are assuming. Let's assume at, okay, let's assume, right? What we are assuming here, the concentration of the p type, okay, the concentration of the acceptor, okay, dopant, the concentration of the acceptor dopant here, okay, Na will be equal to 10 to power 16 centimeter per cube, sorry, per centimeter. Is the concentration of the acceptor here, acceptor atom. This is the pp, and intrinsic carrier concentration is, let's see, 1 into 10 to power 10 per centimeter cube. Okay, so as we know that from the here, in any semiconductor, okay, not the degenerative type semiconductor, okay, it's not applicable for degenerative type semiconductor. For any semiconductor, the concentration of the electron and the concentration of the hole will be constant at a constant temperature, okay, and this constant will be equal to the Ni. So from here we can say that, okay, N, the concentration of the electron will be equal to the Ni square divided by P and Pp, okay, and this will be the 10 to power 20, okay, upon 10 to power 16, and this will be equal to 10 to power 4 percent, right? Now let's what we, this is at the when the VGS will be equal to 0. Now what we are doing, we are increasing the gate to the source voltage. Now we are keeping this gate to the source voltage at 0.1 volt. First let's see, first see here, when we have kept this VGS equal to 0 and VD also 0, VDS also 0, only the depletion region will be present here, okay, and the concentration of the, okay, the concentration of the hole in this p type substrate is 10 to power 16, and the concentration of the electron in this p type is 10 to power 4, right? Now when the VGS will be equal to 0.1 volt, or we increase the VGS by the small amount, okay, so we have applied the positive terminal, positive voltage here, so this will be the positive, okay, and the charge polarization will be happen here, so this will be the negative because of the SiO2. This is the property of the dielectric, and this will be the positive. Hence this will attract, okay, this will attract the electron, okay, near the SiO2 interface, near the silicon die interface, okay. So the electron, so we can say we will make this electron by the red color, right? So this electron, okay, this electron will be come to here. So this electron, red color, will be come to here, okay, this electron will come here. This electron will come from the source and from the drain, because the source and the drain having the large amount of free electron, and some electron is also come from this p type substrate, okay, p types, right? So so the number of the electron, okay, the number of the electron is increasing near the SiSiO2 interface. Okay, now because of increasing the concentration, okay, the concentration of the electron here near the SiSiO2 interface, okay, the concentration of the hole will decrease, okay, the concentration of the hole decrease here, because as we know that in any type of semiconductor the Np equal to Ni square, right? So let's see here, let's assume the concentration of the hole is decreased to is decreased to is decreased is decreased to, okay, 10 to power 14 centimeter cube, decreased to 10 to power 14 per centimeter cube. We can use per centimeter cube, like right here, like here we can write, or in centimeter minus q, okay. Hence the concentration of the electron, okay, near the SiSiO2 interface, I'm talking only about the near to the SiSiO2 interface. Please, okay, please listen carefully here. I am only talking about the surface, okay, the surface, this surface near the silicon dioxide, okay. So here the number and the concentration of the electron will be Ni square divided by pp will be equal to the pp. We can see here the concentration of the hole, okay, near the SiSiO2 interface, and this will be equal to the 10 to power 20 divided by 10 to power 40, and this will lead to the 10 to power 6 per centimeter cube. So concentration of the electrons is increasing here. Now what we are doing, now we are again increasing the VGS to 0.2 volt, okay. Now when we increase the VGS by a small amount, again by a small amount, the more number of the electron, okay, from the source and from the drain will come here, right? Now we have seen that when we are increasing, okay, when we are increasing the VGS, okay, the large number of the electron is coming here from the source and the drain, and also from the body or the substrate. So large number of the electron are coming here. Because of this, the concentration of the electron near the SiSiO2, or this electron is a free electron, remember, okay, the concentration of the electron near the silicon dioxide interface is increasing, and the concentration of the hole is decreasing here. Now let's assume the concentration of the hole is decreases to how much, 10 to power 12, okay, per centimeter cube, and the concentration of the electron here will be equal to 10 to power 20 divided by 10 to power 12, and will be equal to the 10 to power 8, okay, per centimeter cube. Now again we are increasing, this, now again we are increasing this, what, VGS. Now we are increasing this VGS to 0.3 volt, and see here, again when we have increasing the VGS to 0.3 volt, again more number of the electron, okay, the more number of the electron, okay, the more number of the electron will come from the substrate as well as from the source and the drain, okay. The more number of the electron will be come here, and hence the concentration of the electron are still increasing, okay, near the SiSiO2 interface, and the concentration of the hole is decreasing near the SiSiO2 interface. Now let's see the concentration. Let's assume the concentration of the hole which decreases to the 10 to power 10 per centimeter cube. Okay, now the concentration of the electron, okay, near the SiSiO2 interface, silicon dioxide interface, is 10 to power 20 divided by 10 to power 10 will be equal to 10 to power 10 centimeter cube. Okay, here I am writing the another case here. Okay, let me, okay, now I am writing the another case here. Okay, when we have increased, okay, when we have increased the VGS, okay, VGS to 0.4 volt, okay, 0.4 volt, then again the concentration of the electron will increase here. Okay, and this electron, this free electron will become from the this substrate or the body. Okay, so let's assume the concentration of the hole is decreasing near the SiSiO2 interface, and it will be become 10 to power 8 per centimeter cube, and the concentration of the electron will be equal to 10 to power 20 divided by 10 to power 8, and this will be equal to 10 to power 12 centimeter per centimeter cube. Now once again we are increasing the value of the gate to the, again we are increasing the value of the gate, we have increased to 0.5 volt. Now again the more number of the electron, again the number of the electron, okay, the concentration of the electron will be increased here. Okay, will be increased here. Okay, near the SiSiO2 interface, near the SiSiO2 interface, the number of the electron will increase, and hence the concentration of the, okay, concentration, or we can say number, because we are talking about this many volume. Okay, and the concentration of the hole will be decreased, and it will be become 10 to power 6 centimeter cube per centimeter cube. Then the concentration of the electron near the SiSiO2 interface will be become 10 to power 4, okay, centimeter cube. So see here, the concentration of the electron, the concentration of the electron here near the SiSiO2 interface, okay, will be equal to 10 to power 4, sorry, not 10 to power 4, it will be 10 to power 20 divided by 10 to power 6, that will be 10 to power 14. Okay, it will be 10 to power 14, not 4, 10 to power 14, right, 10 to power 14 per centimeter cube. Now let's see the another now let's assume the VGS is again increasing, and it will be go to the 0.6 volt, 0.6 volt, and again the concentration of the electron will be increasing here near the SiSiO2 interface. Okay, the concentration of the electron will increase here. Okay, now, and the concentration of the hole near the SiSiO2 interface is decreasing. Now let's see, let's assume the concentration of the hole here, okay, near the silicon dioxide interface will be 10 to power 4 centimeter cube per centimeter. Now the concentration of the electron will be equal to the 10 to power 20, okay, divided by 10 to power 4 will be equal to 10 to power 16 per centimeter cube, right. Now see here, the concentration of the hole, sorry, the concentration of the electron here will be how much, 10 to power 16. Okay, now see, the concentration of the electron near the SiSiO2 interface is 10 to power 16. okay, per centimeter cube, which will be equal to the concentration of the whole, which will be equal to the concentration of the whole that was present in the substrate. Okay, now at this point we will say the inversion occur. Why the inversion? Because here the majority charge carrier, okay, the concentration of the majority charge carrier, okay, or we can say the concentration of the minority charge carrier, that is the free electron near the SiO2 interface, is equal to the concentration of the majority charge carrier, that is the whole, and this will be equal to the 10 to power 16 centimeter cube. Okay, and this is called the inversion. Okay, this is called the inversion. Okay, this is called the inversion. And when we apply the voltage, I am writing here, and when we apply the voltage at the gate, okay, at the gate greater than the 0.6 volt, okay, then the sufficient amount of the electron is presented here, is sufficient amount of the free electron is presented here, and we can say the channel is created. The channel is created when the VGS is greater than this 0.6 volt. Okay, right, and this voltage 0.6 volt is called as the threshold voltage, and we are denoted this by the VT naught. Okay, VT naught. So what will be the threshold voltage? See here, what will be the threshold voltage? Threshold voltage is the voltage at which the channel is created. The channel is created between the source and, so we can once again, okay, tell the threshold voltage is the voltage at which the channel is created between the source and the drain. Okay, and this voltage is denoted with the VT naught. So when we increase the gate voltage beyond this VT naught, okay, beyond this VT naught, the large number of the electron, that is the free electron, will be, okay, present here near the SiO2 surface, okay, silicon dioxide surface, right? And once we provide the potential difference, okay, let me use this color, let me use blue color. Okay, when we apply the potential difference between this and between source and between the drain, okay, when we keep this drain at the positive potential and this source at the negative potential, electron will feel the electric field effect, and which will start moving in opposite direction of the electric field. Okay, it will be a start, okay, flowing to the opposite direction of the electric field, right? So this we are going to discuss in our next lecture, right? So in this lecture we have discussed about the three-dimensional structure of the Mosfet, okay, and we have discussed the in this lecture we have discussed the three cases. The first case is when we have kept this both VGS and the VDS at 0, and this is called the depletion region. And when we are keeping the VGS at 0 and we are increasing the VDS, then only the depletion region near the drain is increasing. Okay, the width of depletion region near the drain is increasing. Now our second case is when we are increasing the gate to the source voltage and we have kept VDS equal to 0, right? So in this case, the concentration of the electron, the concentration of the free electron near the SiO2 interface is increasing, and the voltage at which, okay, the voltage at which the concentration of the electron in the concentration of the electron in the channel, or the concentration of the electron, okay, near the SiO2 interface will be equal to the concentration of the whole, okay, of the substrate. Then this is called as the inversion occur, and the voltage that applied for getting the channel or getting the inversion layer here is called as the threshold voltage, right? Threshold voltage, right? So in the next video we are going to see our fourth case, right? So because this video will be long enough, okay, and that's why I am ending this video, and in next video we will start with the our fourth case. Okay, thank you.